Hey everybody, this is Alex Merced from alexmercedcoder.com, and this video is going to be on understanding data structures. So this is not necessarily going to be on coding data structures. I do have some videos where you can see me like code out some of these in JavaScript. But the point of this video is more to kind of appreciate like what they are and why they matter. Because I think a lot of people like who come from like Ruby, Python, JavaScript will oftentimes like learn about data structures, but not really appreciate like why they need to know them or like what is their value proposition. And to really appreciate it, like you do kind of have to dive into like lower level languages. Like if you ever dabble with the language C, it becomes like very clear why you need to know these languages, because basically how you structure your data, or the ways you structure your data and the ways you manage your memory are kind of all on you. So like in C, you have to manage your memory. You create like arrays are very limited. You pretty much have nothing else, so you have to really kind of construct the tools you need to make the things you want to make. Okay, so that's reason number one. When having no data structures out of the box, because again in Python, Ruby, JavaScript, PHP, pretty much every other language other than like C and C++, you have a lot of structures available to you out of the box. Okay, in JavaScript you have like objects and arrays, and you have maps and sets. In Python you have dictionaries and lists and sets and tuples. And then in like Ruby you got hashes and arrays, and PHP you got arrays and associative arrays. So you kind of gotta have these structures built. Basically, like underlying these things that are in those languages are these structures, okay? And also things that we interact with use these structures. So understanding like how these structures work and how they interact with memory can allow us to interact with the things that use these structures better to make better code. Okay, so this is just kind of like the larger understanding of why, some context. So first let's just talk about like memory, okay? Why do we care about memory? Okay, and when I say memory, I don't mean like your hard drive. Okay, so I don't mean like that, let's say 60 gig hard drive, whatnot. Because when you're a computer, it's kind of like you have your long-term and your short-term memory as a person. Now, generally when you're doing like your immediate thoughts, like right now, my brain's like having a lot of thoughts. Okay, that's not happening in my long-term memory. Think of your long-term memory as like your hard drive. Like that's the stuff that's there, that it'll be there and you can grab it when you need it. But you have a space in your brain, that your short-term memory, that is handling all the processes you're doing right now. Okay, so this is why like generally like you forget most of the things you just did, because you don't necessarily store all that on the hard drive, aka your long-term memory. Okay, so basically you have sort of your dashboard for doing whatever you're currently doing, your short-term memory, and then some things get saved for later use in your long-term memory. Unfortunately, we don't have like complete control over our brains to be able to decide exactly what ends up being stored in that long-term memory. There's no save button or delete button to get rid of memories we don't want. That would be pretty cool, but the analogy kind of still applies. It's just we have this sort of like not quite as explicit control over our brains. So basically when we talk about memory, we're talking about what's called the RAM, the random access memory. Okay, so whenever I talk about memory, I'm always talking about the RAM in your computer, and your RAM is like the short-term memory of your computer. So that might be like 4 gigs of RAM, 8 gigs of RAM, 16 gigs of RAM, 32 gigabytes of RAM, 64 gigabytes of RAM. It always doubles. That has to do with just sort of like the way bytes and stuff work. I'm not going to get quite into that. Okay, but we're talking about your RAM. Okay, and your RAM is limited. So again, you might have 4 gigs, 8 gigs, whatnot. So especially if you're talking about like machines with less RAM, less memory, being able to not use as much of the available space becomes more important. Okay, so when you're programming like something for like a Raspberry Pi, which is going to have a much lower memory than let's say like my 64 gig RAM laptop, which you know is going to have more memory than necessary. Like I barely scratch the surface in memory usage. But a lot of devices don't. Your phones may not have as much memory, especially like cheaper phones. You know, even smartphones just a few years ago had pretty low memory. So you have to kind of really be efficient with how you use that memory. So that's what we talk about, like space efficiency. Like, okay, how can I write my code to use up as little of this memory as possible to do a simple thing? Okay, I could write code that does a thing but uses up this much memory. Okay, or I could write the code that does the same thing and only uses up this much memory. Okay, so we care about that. Also, it's not just the amount of memory you use, but like memory has like it's physical. Okay, and really what it is like a RAM chip is essentially like a bunch of little like electrical impulses that are on or off. Okay, and essentially like you're changing the state of them. But at the end of the day, like your computer does have to sit there and like look, step by step, look across this field of data to find the particular piece of data that you want. So if I need data from here, and I need data from here, in order to get all the data I need, my computer would have to start here and then move and look all the way over here. That's referred to as traversal, when you're moving across your data. Okay? So also the way your data structures will also determine sort of like where physically your data is relative to each other. Okay, like data here, if I need these two pieces of data here, that I'm going to be able to collect these two quicker because they're right next to each other versus here and here. Okay, so you have these two elements of memory you're kind of trying to optimize. Space, meaning like the amount of memory you use, and then traversal being like, okay, the time that it takes to traverse my memory to get all the data that I need. Okay, and basically these two things are at your concern as far as how fast your program is going to run. Because again, space, well, if you use up a lot of memory, your program is going to be slow because it'll have to wait for memory to free up before it can take on the next piece of data. If you're spending a lot of time traversing your memory, well, that just means there's more processes that your processor is running that slows things down. Okay? So moving forward. But the thing is that like not all memory is created equal. When your computer is like running a program, okay, there is, and actually let me reverse the shape of these things. Let me put this on, because technically this is going to represent the heap. And let me grab the stack, and then this will be the stack. That way it's like stack versus heap. But essentially, like your let's say 8 gigs of RAM or your 16 gigs of RAM, it's split up between something called the stack and something called the heap. So the stack is really going to be our first data structure. And the way to think of the data structure of this data structure is like a stack of pancakes. So when I open up a program, like literally every program on your computer is essentially a function. That's why if you've ever used like a lower level compiled language, like a C, C++, Go, Java, C#, they generally all start with like a main function. Okay, what is this main function? Well, the idea is that the main function is a thing. When you execute your program, like I execute software created in anything, what I'm doing is I'm executing the main function. Now in higher level languages like JavaScript, Python, Ruby, this is kind of assumed. So it's kind of like you're writing what's inside the main function, essentially. Like your entire script isn't already inside there by default. So that's why you don't have to explicitly write a main function. Which implies certain things we won't get into. Okay. But essentially what happens is like, again, I open up, let's say Adobe Photoshop. That's going to open up the main function. So a function ends up being put on the stack. Okay, now then this main function will run the program. And that program will be made up of more functions. So we'll say like, there's function 1. Okay, so basically main is executed. Main's not done executing until you close Adobe Photoshop. So then let's say I do something and that triggers function 1. So that gets put on the stack. Okay, each function is being allocated a space in memory. Okay, but again, this concept of a stack is the idea of, again, think of a stack of pancakes. Every time I add a pancake, it goes on top. Okay, so again, if 1 executes some other function, okay, and now the pancakes, when I eat pancakes, I don't eat the pancake on the bottom, I eat the pancake on top. So generally, like, you add pancakes by putting them on the top of the stack, but then you eat pancakes by eating the pancake that's on top of the stack. So essentially, main and 1 will remain on the stack until 2 is done executing. So once that function is done, that space in memory frees up. Okay, now let's say another function gets executed, so 2 is now off the stack. Now the 1 function continues, and now it executes another function we'll call 3. That gets put on top of the stack, and then maybe 3 executes another function called 4, and the stack keeps building up. And then again, main doesn't resolve until all the functions on top of the stack. So basically, the last thing on the stack has to be the first thing off the stack. It's last in, first out. Okay, so that's sort of the moral of the story when it comes to stacks. Stacks are last in, first out. And that's all fine and good. Okay, so whenever you think of a stack data structure, always just think first in, first out. I mean, last in, first out. Oops, yeah, I wrote last in, first out. Okay, so main, 1, 3. Again, 4 would have to finish first, then 3, then 1, and then main can then complete executing. Now, the great thing about functions on the stack is I don't have to, me as the coder, I don't have to explicitly like clean the memory. Why? Because the minute 4 is done doing its thing, it will erase itself, and now that memory is freed up. So I don't have to do anything to manage that memory. Okay, so this is kind of like where like functional programming, this style of programming, becomes sort of kind of cool, because like if you can write it in a sort of like unidirectional functional way, you end up doing most of your code on the stack, and you're going to end up needing this heap thing very little. Okay, so but again, that's what this stack is. So whenever you think of a stack in code, it's always just again a structure of data where you add things to the top, but the thing on top goes out first. Last in, first out. One of the most important applications of this stack idea of a stack is the stack when it comes to your memory. Okay, your memory stack. And then again, if too many things are on the stack that your memory doesn't have enough room for it, that is what's known as a stack overflow. So now you know where that term comes from. For all those who've spent as much time on Stack Overflow as I have. Okay, but now here's the thing. Maybe 3 is going to create some data, and that variable needs to be available to 1 when 1 continues. The problem is, if 3 is finished, then 3 is going to get erased. So we can't store that data in the stack, because again, the stack will clean out that data the minute 3 is done. Okay, these are essentially all your local function variables. Okay, so as soon as this function's done, it cleans it up. So in C, like if you're in the C language, what would have to happen is that this, because this isn't done automatically for you, I would then have to take that variable, okay, and let's say I need this data takes up 2 spots. I'm going to allocate some data on some variables, some space of memory on the heap. So that's what the heap is. It's just it's a heap of data that's got no particular order to it. Okay, I'm just going to say, okay, here, allocate some space for the data, and then I save the data in that allocated space. So that way when 3 is finished and 3 gets erased, this doesn't get erased because it's not in the stack. It's not there. So in that case, 1 can then go back and then fetch the data that was stored there. Okay, this is what makes programming in C so hard, because you have to actually think through that. You got to think, okay, well, this function needs that data, so let me go allocate some space on the heap, stick the data on this, put that data on the heap, and then the next function can then go fetch it, and it gets pretty complicated pretty quick. Now, again, in lower level languages, I mean higher level languages, again, higher level means less complicated, lower level means more complicated. That's a simplification of what it means, but in a higher level language like Python, JavaScript, Ruby, that's taken care of for you. Okay, the interpreter for JavaScript, for Python, for Ruby will determine whether the memory can stay on the stack or on the heap. You don't have to think about it. You just write your functions, you just write your code, and it figures it out. So in C, what would happen is that once 1 is done with this memory, I would have to actually write a line of code that says, okay, deallocate this memory. Let's delete this. Let's clean up the stack. Clean up the heap. Okay, and then we would clean out that memory. In Python, Ruby, and JavaScript, instead you have this like thing that's kind of running at the same time as your program or along with your program called a garbage collector. So as functions get complete, the garbage collector is going to keep monitoring the heap to see if there's anything we can clean up. So that way you don't have to worry about managing between the stack and the heap in your computer's memory. That's pretty cool. Problem is, again, more processes for your computer to run, which affects like slowdown, because now periodically, maybe after every function call, I don't know what the exact algorithm is, but ever so often the computer's going out and taking a look, hey, should I clean these out or not? And again, for most computers nowadays, it's probably not much of an issue, but again, this starts to really matter when you're talking about like really low memory devices. Think of like a vacuum cleaner that might have like some smart features. You really need every bit of processing power and memory you can have, which is why they'll still use languages like C. Languages like Go and Rust are trying to kind of offer friendlier alternatives to have those kind of faster, more memory efficient programs. But at the end of the day, like C is still sort of like, hey, I need to go program something for like a very, low-tech watch. Probably gonna have to do it in C because you have full control over like how the memory usage is there. Okay, so hopefully this gives you a little bit of appreciation for like how memory is handled. Okay, and again, having that perspective like of that level of manual managing of memory that's in C will help you understand like why do C programmers really care about having to be able to construct these data structures, but at the same time, you understanding how the stack works, even though you don't have to manage that memory in your code in JavaScript, Python, and Ruby. Understanding that you can write better functions, because then I can know, okay, hey, let me try to write functions in a way where local variables are local and global variables are global, so that way I don't cause the garbage cleaner to have to do much, or the garbage collector is the actual term, garbage collector, have to do too much work. Because if I can write code where the garbage collector has to do little as possible, it's going to run faster because the garbage collector does less. So, understanding that can help you write better code. Okay. Cool. Okay, this is actually supposed to say processor. So here we're talking about a queue. It's another data structure. Now a queue is more like a line in a theme park. So again, while a stack is like a stack of pancakes, everything stacks on top of each other and then we pop out whatever's on top. In a queue, someone enters through the back of the line. Okay, so let's pretend I have data 1, data 2, data 3, data 4. In this case, we're talking about processes. So basically what happens is that the way your processor works in your computer, it works in a queue. So what is the processor? So in the same way your RAM is kind of like your short-term memory, your processor is like the part of your brain that's actually doing the thinking. It's actually running calculations in your head and whatnot. Okay, so think of the processor as like the brain, the RAM is like your short-term memory, and your hard drive is like your long-term memory. Okay, so then what happens here is that all the instructions, your brain, your processor, can only take in one instruction at a time. So all the different instructions that all the different programs in your computer are trying to send over, okay, are being stored in a line. So like the first instruction to arrive is at the beginning of the line, then the next one, then the next one. Hey, a new instruction comes in and it goes at the end of the line. The question is, when do you leave the line? So if this was a stack, the thing that came in last would be the first thing out. But a queue is the opposite. The first thing in is the first thing out. Okay, so queues are FIFO, first in, first out. So what's going to happen is the processor will run the first process, then run the second process, and then new processes will keep getting in line, kind of like an amusement park ride. And they're all in line to go ride the processor. Okay, but again, your processor can only run one thing at a time. Although, nowadays what happens is that instead of having faster processors that can run things faster, you're trying to have what's called a multi-core processor, where it's really like multiple processors. So it's more like if we did like a quad core, if you ever hear that term, quad core processor, would be this. 1, 2, 3. If we did this. Actually, let's maybe stretch this out a little bit more. And let's copy that. And then we'll put 1, 2, 3, 4. So see, I have quad cores. And then now each one has its own line. its own queue of things waiting, of instructions waiting to be processed. So now I can do 4 times the amount of work, even if all the processors are operating at the same speed as before. So essentially I can do more, even though necessarily like my gigahertz isn't necessarily faster. Okay. Now this issue is like, okay, and then this is sort of like a big issue right now with like a lot of programming languages. Like, how do you, in a programming language, express your program to take advantage of this? Because right now, most programming languages are essentially like single-threaded or single process, built for a single thread, which means they're just sending one set of instructions to one processor or one core. So the magic keyword, when you hear like people talk about this, like, what is this thing? This is called concurrency. How can I split up my thing? How can I split up my thing to be able to take advantage of these multiple cores? So there's languages like Elixir and Erlang with the Erlang virtual machine that, you know, are really kind of built to take advantage of this. You can actually say, hey, okay, let me create a new thread, and anything for this thread goes here, for here. I think Python is kind of added something for that too. JavaScript is still single-threaded. But there's different ways that they deal with this issue of concurrency. How can I make sure that multiple things in my software can happen at the same time to speed it up? Okay, so just to recap, a queue is, again, think of it as like a line to the processor. Okay, a line to the processor. But again, now we have multi-core processors, and we're learning how to help programming or code to take advantage of multiple cores, and this issue is referred to as concurrency. Cool. Now we go to arrays. An array of data is just a bunch of data in sequence. Okay, so if you're in JavaScript, Ruby, you're probably used to arrays being super flexible and amazing. But if you're like in C, C++, Go, Rust, again, the lower level languages, arrays are literally a sequence in memory. So imagine that I'm going to store 5 numbers. So what I'll do is I'm going to block off 5 spots for my 5 numbers. So I haven't even stored the numbers yet. I actually have to sit there and say, hey, I want 5 spots. And then it's actually going to block out a 6th spot. Okay? So it'd be really, I'm going to store, like, let's say the number 1 here, the number 2 here, the number 3 here, 4 here, 5 here. And then in the next block of memory, it's going to make some sort of like sign that basically means here's where the array ends. So that way, like, the software knows, okay, hey, here's where this array of numbers ended. And really all the value of the array is, it's really just a pointer to this first value. Okay? So when I use that variable that is an array, it's not actually like holding the 5 pieces of data. It's just saying, hey, okay, so let's pretend like, let's actually like do a thing here. So let's say I created a variable. We'll say like an integer of, and again, doesn't matter what language is. I'll just kind of write it in sort of like a Go syntax. Var. Actually, I'll just say cheese equals, okay, an int array with 5 spots. Okay, this is kind of how you would kind of write it in Go. 1, 2, 3, 4, 5. Okay. So I'm saying, hey, cheese equals an array with 5 spots, so it'll allocate the 5 spots, and then again gets that little space of memory to kind of mark the end of the array, and then says the 5 things, the data in those 5 spots are 1, 2, 3, 4, 5. Okay, cool. Now normally, and you'll notice this in pretty much all programming languages. Okay. Usually, if I want to access the first thing in that array, I would say cheese 0. Okay, and this is always something like if you're new to programming, like this always boggles the mind. It's like, why do we start from 0? Why don't we start counting from 1? It's actually a pretty good reason. Because if cheese points to the first spot, the location of the first item in memory, basically I'm saying is that I want the item in the cheese array that is 0 removed. So this spot plus 0 is this spot, 1. And then if I were to say, hey, get me the spot, get me the cheese array, so I have to start here, get me the item that is 1 removed. That's this item over here. Okay, and then I say, okay, let's go to 2. So we start here at the beginning. And we say 2 removed, 2, 2. So that's the third item. Okay, so that's like the reason why indexes are zero base, because they don't represent like the numerical order. They're representing how far they removed from sort of that initial pointer in memory. Like that's sort of like where that zero base index comes from. Okay. But again, these can be pretty fast to traverse because look, all the data is like literally next to each other. Okay, that's pretty nice. Okay. Problem is, I have to, in a traditional array, so if we're talking about like languages like C, C++, Go, Rust, that are lower level, when I declare an array, I get this sequential block of memory to hold the date, the 5 numbers that I wanted, but I can't add a 6th number because there's already a marker here not making a 6th spot available. And that sounds like probably mind-boggling if you're mainly like a Ruby, Python, JavaScript developer, because in there you can just like add an item to an array like whenever you feel like it. Like you don't have to think about it. You're just like, let me just push or append something to this array. Huzzah! Because technically what you're dealing with isn't necessarily an array under the hood. Okay, like in a proper array is essentially, you allocated a certain amount of space of memory sequentially, and you can access them this way. So like that's all fine and good. But what if I need something a little bit more flexible? This is where we get to linked lists. Now let me just talk about what pointers are. I did mention pointers a second ago, but all a pointer is a value, like a piece of information that isn't like a number, like 1, 2, 3, or a letter. What it is, it's an address to another spot in the memory. Okay, so imagine, if I went to a house, or like someone said, meet me at this address, and then I get to that address, and what's there is not a house, but a piece of paper that says, no, actually meet me here. Okay, now I go drive to that other house. Okay, that's what a pointer is. It's not necessarily your destination. You go there to figure out where your destination actually is. So the variable that generally holds an array isn't the array itself, it's a pointer to where that array exists in your computer's memory. Okay, so linked list, what we do here is like if I want to store, again, 1, 2, 3, 4, 5, I'll store the data there, but then it's preceded by a point afterwards there's a pointer. So then what happens, this pointer will point to wherever the next piece of data is. So the benefit of this is I don't have to lock in a sequential stack of data. Okay, I can add stuff. So later on I want to add 2. I will just say 2 pointer. So now this pointer over here points to 2 over here. And now we have a spot for the next pointer. So then later on I want to add 3. Then there's another pointer. Okay, and then 4. Then there's another pointer. And then we'll say 5 and another pointer. Okay. And actually, technically, I might not have a pointer on 5. Okay, depending on how efficient I want my memory to be. Okay, like a straight up linked list would just be like that. Like I always got to start from the first thing. Okay, so I'm still like saying, hey, like 0, 1, 2, 3, 4, like how many times am I removed? The difference is I'm getting to the next one via the pointer. Problem is I'm taking up double the memory because I have to allocate memory for each of these pointers. Okay, so I'm using additional memory. There's more time to traverse because I have to travel from here to here, then to here to here, versus the sequential pieces, which were faster. But again, this is more flexible. So I might just want to do it this way, so I can go from 1 to 5, but I can't go backwards. Okay. You could do a circular linked list, so that means I do put the pointer at 5, so that way from 5 I can go back to 1. Okay, and I can do a doubly linked list, where basically there's also a preceding pointer that points backwards. Okay, and then I would theoretically have a spot here for a pointer before 1. So essentially, this pointer points back to 1, but then this pointer points back to 4. But you see, the more complicated the more flexible I make that linked list, the more memory I'm taking up, and the less memory efficient it has. I'm not 100% sure if like an array in JavaScript, Ruby, or Python is set up as a linked list. I imagine it is. It might be a linked list, or it might. There's other ways they could have handled it. I don't know. I think in JavaScript it's actually like a class. It's actually like an object. Um, but let's not go too far down the rabbit hole. Again, there's in higher level languages like JavaScript, Python, and Ruby. There is sort of the data structures that you use when you use those languages, but then there's a reality of how they're implemented. Because oftentimes, like the interpreters for those languages are created in C. So someone in C had to like think through like, okay, how am I going to do this? Now, if you're using Deno, which is like a newer JavaScript runtime, that was built in Rust, but they still have to kind of think through the same things. Okay, so that's like what a linked list is. It's essentially an array. You have like data in sequence, but they're scattered across memory, and they take advantage of pointers to kind of know where each other exists. Okay, and again, what's a pointer? It just points to where something is inside your memory. Okay, hash lists and hash maps. Okay, so a hash list, again, is just anytime you see the word list is another word for array, so that's why like in Python, arrays are referred to as lists. But a hash list, what is happening here is you're saying there's sequential data that you have, okay, but you have like a top hash, which is sort of like, and the hash is really just like a sort of just think of it as like a jumble of numbers and letters. It's just like a unique jumble of of characters to identify something. So you have this hash that kind of identifies the thing, and then what's going to happen is that each of the indexes include the top hash and their own hash. There's a couple different ways you do it, but the idea is that like the index has to go through a hashing function, and that hash function encrypts the thing. So basically what it's doing, it's taking this original hash, this top hash, and the index, putting it through the hash function, and essentially like that is like becomes these things put together help identify like where that data is in memory. This is used for this particular like structure is kind of used a lot for like files. When you download files on the internet, okay, you are downloading files in blocks. So you have like little data blocks, little packets that are coming in piece by piece. And the thing is that you might be getting all sorts of different data from the internet, and you want to make sure that you're building the right thing. So each file is essentially a sequential array, sequential blocks of data, essentially an array or a list of data, and you want to make sure that you put them all together in the right order. So every block that comes in has a hash, and that's how the computer is able to identify like which blocks belong to which lists. Okay, through that hashing function, they're able to say, okay, hey, I've collected like, the things that are coming in belong to this file that I'm downloading versus this file that I'm downloading versus that file that I'm downloading. So this kind of acts as a way of creating an array, but an array where you can kind of like identify like multiple different type lists of data that are coming in. A hash map is a way, again, at the end of the day, like they're really like, you might be aware of like a hash in Ruby or a dictionary in Python, or an object in JavaScript might be a little bit different. It's not quite a hash map, but or associative array in PHP, or literally a hash map in C# or Java. But essentially what this is, it's essentially an array. Everything's an array. Okay, there's no alternative. But the idea here is this. What a hash map does, it allows you to identify where you're storing your data through some sort of string. So I'm going to say, hey, a name, and that name then gets passed to a hash function that uses a mathematical computation to determine an index number. Okay, and it tries to figure out like a unique index number. Okay, so that way, like the same piece of data will always, the same key will always be stored in the same index. And what happens if two possible words end up with the same number? There's a couple different ways you can handle that. You can actually have like a linked list underneath but okay. So, but the idea is that basically what's going to happen is it's going to say, okay, hey, the hash function calculates a number and determines that like this index here, this location in memory here belongs to, is what this hash function identifies. So it says, hey, whenever you use name with this hash function, it's going to identify this index. And same thing with age. So essentially it's creating an array that I'm allowed to use strings to identify which piece of data that I want, and through the hashing function it determines the index. And because of this actually really gets the data really fast, because I don't have to traverse, like I don't have to go 1, 2, 3, 4. I just say birth year, and the hash function is going to determine the exact location in memory where that data is going to be. So I never had to start from the beginning. Okay, essentially like, yeah, I mean it's, you still like essentially like a variable for a hash map is still pointing to where like the sequence in memory exists, but the hash function is used to identify like exactly where that location is going to be. So it can actually operate quite fast relative to other ways of kind of doing that. Okay, so that's all that is. So a hash map, again, is underneath it is essentially an array, but you are using strings to identify which items in the array you want, because the hash function is able to identify like what the index would be, the actual like numerical index would be. So this is like why they call them an associative array in PHP. Cool. So that's that data structure. And then last for today's adventure is trees. Okay, now trees trees are a way of structuring data in a way that, like, if you have a lot of data, you can get to it pretty quickly. Because imagine if this was an array of 0 through 6, okay, I would have to traverse from 0 and go 0, 1, 2, 3, 4, 5, 6. But here I can go from 0 to 2 and from 2 to 6. So it only takes me 2 movements to traverse the data to get to that particular number. Okay, and technically, like, if I take a look at starting from 0, there's no more than 2 even though I have 6 pieces of data, there's only 2 steps to any particular piece of data. Okay, that's gonna speed things up, so you can traverse complex data much quicker that way. This is technically how we do like the DOM. Okay, so if you're familiar with web development, there's the document object model. Like, this is the data structure that's underneath every HTML web page that you see. So essentially, like, 0 would be like the HTML tag. Under the HTML tag, there is the head and body tag, and then there's like, other tags under head. So like, let's say like, like a title tag and some meta tags, and then under the body there's some H1s and some P tags, and this tree kind of builds up from all these HTML nodes. And the beauty of that is, like, I can start from here and get somewhere in the body a lot quicker because I don't have to pass the head. Like, I don't have to go explore all the different tags inside a head to get to the things in the body. I can just be like, okay, HTML body, let's say H1. Okay, so it allows me to traverse that large data structure, in which DOM trees can be quite large because HTML sites can be very complicated nowadays. It allows me to traverse it very easily and efficiently relative to other structures. Imagine you had an array of your DOM nodes. So you would have to go from HTML, then through all the head, and then all the children of head, and the children of those things, before you get to body. Okay, that wouldn't necessarily be the most efficient way to handle that data. So always think of just generally like information that can branch, where you have like really large sets of data and you're just trying to kind of minimize, and you can sort of relate them in this kind of way. Like, you could do this with numbers. Like one way this could have been done is that we start. Let me like rearrange this. We'll start with the number 4. Okay, and then put numbers below 4. Let me see here. Actually, we'll put here like the number 2, and then here we'll put the numbers 2, 1, and 3. Because, hey, I go here and I say, well, the number I'm looking for is definitely less than 4. Okay, is it higher or greater than 2? Okay, so the number I'm looking for is 3. Okay, and then here would be, let's say, the numbers I have left, 1, 2, 3, 4. Let's say here, I must have had some number twice, so I had 0 before. Okay, so then here we'll put 6, and then higher than 6 is 7. So this is kind of like of a balanced tree. So the idea here is this, and this is also actually a good way of like, this gets into like how some sorting algorithms are done. You know, where basically you can like, I forget, like some different divide and conquer strategies. But the idea here is like, again, I can get to 3 pretty quickly because I know if I want 3, 3 is less than 4, and 3 is higher than 2, so the 3 must be stored here. Okay, and you can traverse your tree of data a lot quicker in this manner. So it's just another tool in your arsenal of how you can structure your data. So all of these are actually tools you can use to construct your classes. So like in any language, when you construct the custom object, you may want to create something that works like one of these data structures to help implement the thing you're trying to create. Whenever I say implement, it just means like take something in your mind or something that you know you want to do and make it an actual code. So basically, if I were to implement a tree, it just means, hey, code the tree and make it like a thing that's actually working in code. Yeah. Okay, I think we covered a lot of material in 40 minutes, so I'm going to leave it at that, but hopefully this helped you understand a lot of cool things. My name is Alex Merced from alexmercedcoder.com. Head over to devnursery.com, join the Slack and Discord community, follow me on Twitter, add me on LinkedIn if you haven't already, subscribe to this YouTube channel. Make sure you can check out all my libraries over there, mostly JavaScript libraries over there at alexmercedcoder.com, and my lots of videos on pretty much any topic you would like to learn when it comes to coding. I'll see y'all later. Have a great one. Ciao.